There we go. It's too much of a pain to get the automated recording. Now I can just have this awkward intro and then post this on YouTube. And now if you missed today or you need to go back to something, I'll try to start linking this on the landing page after the fact. So today we're talking about Carnot mapping, right? This is for assignment 2.2.1, and this is going to be how we can reduce a circuit without doing circuit math or Boolean algebra. Let me click my way in here. All right. The big thing about K-mapping is we're going to be producing something like this and using a technique where we'll like circle elements of it in order to achieve a reduced logic expression. And it's just a graphical technique for rearranging your truth table and then applying a trick. And once you've rearranged your truth table and applied the trick, it's pretty much golden. Like it's going to be the most reduced logic expression. So they work for any number of input variables, but they're really not practical past a 4-input circuit because like these little grids, you'll notice this is a 3-input circuit. Well, if we go to 4, it's a 4x4 grid. And every time we add one, we're just continuing to expand the size of that grid. I one time had a student do, I think it was an 8-input Carnot map, and it was an entire page of paper in tiny text. So
Schrager,
yeah.
Aaron's asking where in the packet all this stuff is.
Page 37 is where the assignment is, and it'll be in the PowerPoint if you scroll through until you get to, you'll just have to flip through the PowerPoint packet till you get to it. I don't remember the page for that.
Schrago, actually, now looking at it, the Unit 2 packet. Oh wait,
There's
no,
no
it
page
does have
numbers.
page number. Wait, no.
They're on the right side. They should be.
Only some of
did
them
they
have
not?
page numbers.
Why?
like-
It's so weird.
But the
They just don't, yeah.
The presentation packet, all of those have page numbers. So I thought you said 37 on that, but actually at the presentation packet it starts page 21.
Well, I don't know why the numbering all got screwed up. Okay, so presentation packet page 21. My digital, for some reason, it was supposed to be printing page numbers, but it didn't. Oh well. All right. So what is going on here with the K-maps is it's just a graphical tool for reorganizing your truth table. And frankly, most of what we have here is pretty crap. So we're going to start with this slide, because this slide is going to be where we're going to walk through what a K-map, how we like rearrange a truth table to create a K-map. All right. So right here, we have the truth table for a 2-input circuit. You'll notice this circuit has inputs W and input X, and it just runs through all the possible combinations. And here we have our outputs, where we have our 1s and our 0s for like the truths of this circuit. What we're going to do is a K-map is going to be a grid laid out like so for like a 2-input circuit. It runs through on one side each of the possible combinations for those inputs. So here we're looking at X is 0, X is 1, Y is, or W is 0, W is 1. And we're just going to start out by building it like this. And I'm going to give you a couple examples because it'll make more sense as we go for like seeing some of the bigger ones. But what we have to do with a K-map is as we move along, only one thing changes at a time. In this case, that's easy to have happen because there's only one input. And we're going to move our 1s over to this new system. And I'll have some guides for you on how to create K-maps. But the gist of it is we're just rearranging. Here is 0, 0. Right? W is 0, X is 0. Over here, W is 0, X is 0. And we're going to look for alignment there. When W is 0 and X was 0, we had a 1. When W was 0 and X was 1, so W is 0, X is 1, that's a 0 in our truth table. W is 1, X is 0. So here's W is 1, X is 0. That's a 1. And then they're both 1s. Those are both 1s. We have a 0 at the output. So far, doesn't seem that handy, right? Like we just like rearranged where we put our 0s. Now it's in a grid instead of like a column. There's a trick. Once we build one of these K-maps, there is a rule to it that says we can circle groups of 1, 2, 4, 8, 16, and we'll just keep moving up in that doubling in our base. It's a base 2 system. And our goal is to circle the largest groupings of that, right? The groups must be in a row or column or in a grid. The groups must be connected. And I'll show you more about that in a second. But they must be connected in some way. We can't circle on diagonals. We'll just have to remember these, and I'll give you some examples in a second. Can't form groups on diagonals. And so here's what we're going to do with this. Before, if we had written out like the logic expression for this, we would have gotten F equals, well, here it's W naught X naught for our first min term, and then, or W X naught for our second min term. And we could go through and we could use Boolean algebra, and we could reduce that expression. Over here, we're going to do this thing with the K-map. This is our new tool, and we'll go and we can circle a group of 1. So I could circle just, a grouping of 1. We're going to circle all of our 1s, all of our truths. And I could circle just one of these, but my goal is going to be to circle the largest grouping that fits the rule of 1, 2, 4, 8, 16, 32, or so on, 1s circled. So I can circle, or I guess I put a box around them, a group of 2 right here, because that's the largest grouping of 1s that are like adjacent to each other and that doesn't rely on like going on a diagonal. So far, you're probably a little confused about what we're doing here potentially, and that's okay. We're going to keep getting some examples, and it'll kind of start to be clear when we see bigger K-maps too. So what that does is when we get to this stage where we've made one of these K-maps and we've circled the section, this is how we're going to do our Boolean algebra. This is what does it for us. The way it works is once we get our circling done, we take that circling and we say, okay, anything that within that circling included a change of that letter goes away. So in the example, for example, in this one, well, that circling all occurred where X was 0, X was not, X not was the only case, right? W, this circling included both W is a 0 and W is a 1. When that happens, we can just remove that from the expression entirely. And what that does for us is we only include things in our logic expression that are in that circle and don't change. W in this one would have changed. We had a W naught and a W. That goes away. And this reduces down to just X naught, because X naught is the only letter in that's like a header for this circle that didn't change what it was. It just remained X naught the whole way through. And so this expression over here simplifies into that. We didn't have to do 9 Boolean algebra steps to do it. We just had to make one of these maps. Do we have any questions right now? All right. We'll keep cruising with this. Just know that the biggest thing with this is going to come from practice. Hope everyone had good weekends. Got to fill the void while I chat and erase things somehow. I also do just legitimately hope people had good weekends. Oh yeah, it's good. Sorry. This slide shows a ton of automated stuff built in. I really dislike this PowerPoint. Basically what this is doing right now is it's showing you possible different ways you could circle, like in K-maps. And so in a K-map like this, right, there's nothing you could circle. In a K-map that looks like this when you translated it, you could only be circling a group of 1 because there's like an isolated 1, right? There's no, like we're circling sets of 1s. And here, like there's only 1 all by itself and you'd have to put just circle it by itself. It doesn't really do anything for you if you have a K-map and you only have a box of 1, because that's just, A, B, not. That's what your expression would have been if you had it in a truth table. Keeps going through. And groups of 2 work like that. You can see you can get groups of 2 in many different combinations. Groups of 4 are just big groupings of K-maps. And I am trying to go through each one of these just to show you, like, we are circling in groupings of this. You cannot circle a group of 3 ones. There's a way to deal with that, and I'll show you in a second, but you can't circle a group of 3. Oh my gosh. That's just a giant wall of text. What I recommend you doing is, like, if you're struggling on a problem, this is a good PowerPoint to come back through, and it's linked in your Buzz assignment to come back to through some of these little groups. Honestly, I just want to go through more examples with you. So if you are taking notes on a piece of paper, I want you to at least get one of these K-maps in there. If you have the PowerPoints, this is, page 11 from the PowerPoint. But what we're going to be doing is we're going to be creating this K-map. And I do need to show you how to make a K-map, because a lot of our problems will either give you a K-map or give you a truth table and ask you to make the K-map. So I know in your upcoming assignment, you're going to have to make a K-map from a truth table. So, like, let's go through that. For a 2-input K-map, right? Or for 2-input truth table, our K-map will be a grid of 4. It's because we have 4 possible, like, combinations. In our left corner, our upper left-hand corner, this is important. We will always start with the nots, the zeros. We're always starting with this term. Doesn't really matter which way you do it. We'll see when I click forward, it's going to fill in for us where they put them. I'm just putting J on top and K on the side. It doesn't actually matter that much. Those are both the zeros I'm starting with. So it's J naught, K naught. And then you're going to put the ones there. And in a second, we'll get another example that's like a 4-input table. And I'll show you how we handle it for a 4-input K-map, because that's where really a lot of this starts. We start to see more of the rules show up. Then all we do, we just go look wherever we had a 1, we'll go plug that in. So when J was a 0 and K was a 0, we had a 1. When J was a 0, K was a 1, we had a 1. We'll plug that in. And the other 2 are zeros. Next step, put a box around your 1s. And then you look for what doesn't change. Here, that box, J naught, never changed. It never became J within that box. So our output F is just equal to J naught. That's a lot simpler of a circuit than originally. Originally, our term would have been J, K naught for both of those, or J naught K. So, like, this is already a much simpler circuit to wire, to build, to deal with than that. It's a powerful reduction technique. Like, that would take you, I think, a lot longer using Boolean algebra to get to here, or it would at least take a little bit of looking at the theorems. This process will work no matter how simple the theorem, or no matter how simple the circuit or how complicated the circuit. So, okay, they did it the opposite of me, but you'll see, like, it doesn't matter which letters you put on which side as long as you stick with your zeros in the first spot. Like, they're still simplified down to J naught, which is the exact same thing that mine simplified down to when I had them flipped. The key is just starting with the zeros and then flipping them after that. All right. So now a 3-variable K-map is going to look a little different. And you'll see this is going to be kind of how it scales as we can continue to get more variables in our K-maps. So if we have a 3-input truth table, what happens is we start out, we have 8 possible combinations. So we have 2 groupings of 4. We'll again start with our zeros in the corner. But this is where I want to just note to you, this is really critical that you see how this is laid out when you're creating your K-map, because this is where I see the confusion come in. Is not at the 2-input K-maps, but when we go to 3 or 4 inputs, how we build that K-map, because it's not as straightforward as you might think. You'll notice here it's Y naught, Y. That's great, right? Like, Y was our last input. We're going to put that one on its own up here. Our first 2 inputs we'll put on the left side here. And what's going to happen is we start out with all zeros, right? We start with this condition. And then you'll notice a lot of people's like gut instinct is to go to WX after W naught, X naught. And we can't do that, actually. Your K-maps will not work out, all right? It's part of the rules of K-mapping. Is one of those rules is going to be that we can only change 1 variable with every row, all right? And this is actually, it's in there on the PowerPoint. If you are taking notes on your own, like in a red text or something, put a star, or if you have the notes, put a star by that section and like an arrow towards that. Only 1 variable can change for every time the row changes. And what that means right here, this is one change. When we go from W naught X naught to W naught X, only one thing changed. When I go from W naught X naught to WX, it's only one thing changing, right? We went from having W naught X to WX, right? Only the W changed there, not both of them. When we go to the next one, it's still only one change because we went from WX to WX not now. Now I'll point out if we had had this table and instead of what is correct right here, we had what the common thing that I see students do that is incorrect is they will go, you know, they'll have W naught X naught, they go W naught X, and then they want to go and they want to do WX naught because that's like the flip of it. They're like, oh, I just want to take care of that and then have just WX plain at the bottom because that like looks cleaner to them. Here's all the zeros, here's all the ones. They have the two possible mix combinations in there. It won't K-map correctly. You won't get the correct circuit simplification. The whole process is based around the expectation that only one variable will change every single row. So once you, and we'll have to build some of these, right? Some of your assignments will just give you this grid and have you filling in these letters here. So here we've got W is 0, X is 0, Y is 0. There's a 1 right there. And then I just go through, and when I build these, I just go and look for where my ones are, right? So here I see, okay, W is 1, X is 0. There's W is 1, X is 0. And then Y is 1. Here's W is 1, X is 1, Y is 0. So W is 1, X is 1, Y is 0, goes right here. All right, you want to see what it looks like? Okay, they go through putting everything in. Here's my favorite thing about these. What? It didn't show it to us? No. We have really weird circlings we can do. Oh, when we have these. I'm gonna erase this quick and then we'll do the, oh wait, no, I don't know why they showed you this one. I guess outside of just showing you that in this one, there's only certain circlings we can do. Like this one's circled by itself. There's not much you can do about that. Like sometimes the only option is to circle something by itself. And that represents that like that min term is as simple as it can get. Like you wouldn't have been able to reduce that part of the expression away if you were doing Boolean algebra. So they're like, oh yeah, here's how to do circlings in a three tier one. You'll notice that. Where's the ones I want to show you? These are the weird ones. All right, this is what I want to show you. So here's what's weird about some of these. You'll notice that we're circling. You can do this, it's a legal move. You can circle around the edges. You have to treat K-maps as being like a ball. The two ends actually connect together. In that case, it's like a ring in that way, but like the sides also connect together. So like this side connects to this side. This side connects to this side. So if you need to, you can actually do a circling around there because here we have a 1 all the way down here. We have a 1 all the way up here. And since only one thing changes when you go from this box to this box, wrapping around, right? We go from A, B naught, C naught to A naught, B naught, C naught, right? There's only one letter difference between this box and this box. We can do a circling around them. And that would then give us F equals B naught C, because within that circling, A had changed. Same deal if it was there. You can do circlings of groups of 4. They can either be a box or vertically. And you can do that same deal around the end because like the key thing here, I think, is remembering that the edges connect like that. All right. So like let's do an example. Let's run through an example again of that one. So here we have EFG. And I'm just going to start, you'll start with your furthest left side. E naught, F naught. G naught. Only one change there. And now as we move down it, here we'll go with E F naught. Actually, let's do E naught F. I like that more. I like to leave my furthest left variable changed the least. So there's E naught F. Then there's E F, because that's only one change, right? We only can change one thing each time. We have E naught F naught, E naught F, then E F. And now lastly, we still need to get the case of E F naught with only having one change. Once you've done that, you'll go through. All right, where E and F are 0, so in this row, and G is 1, so this column, we have a 1. And that's going to be like something to help you remember it as you go along, right? It kind of tells you a row and then a column when you look between your two sections. So here's E and F, this is E and F are 0, that's a row of your K-map. And then G is a 1, that's a column of the K-map. So row, column, that's where we go. Next up, E is 0, F is 1. So here's E is 0, F is 1. G is 0, we'll have a 1. Now we're just going to jump down here. I like to just do all my 1s, get them out of the way, and then fill in the rest with 0s. Here's E and F are 1, so it's this row. G is 0, so it's this column. I skipped one. Here's E is 1, F is 0. E is 1, F is 0. And that's going to be the G is 1 column right here. Go fill in everything else with its 0s. And then we can use K-maps to simplify it. Now you kind of work your way up. I start out by going like, okay, well, I want to get the biggest circlings I can. So where's the biggest circling? And the biggest grouping I see right here is a group of 2. I immediately see, oh, hey, look at that nice group of 2. So I can do a circling there. And then a common thing I see is people will look at it and they'll go, oh, okay, I can only circle 1 there. But if we wrap around from top to bottom, we have E naught F naught G, and then we go around to the bottom, what's E F naught G. So only one thing changed. So we can do a circling there. To write our logic expression, we'll just go to each individual circle and see what it means. So like if we'll start with this individual circling here. I noticed that in that circling, both cases, G is a 0. So G naught remains part of that. And then if I'm looking at over here, well, F remains a 1, but E changes. It's E naught and E within that. So since F never changed in there, we keep F and we'll ditch E because E changed within that circling. Now we have 2 circles to deal with. And so that's going to represent another addition to the expression, right? So this is F G naught, or now we can look at this one. Here we'll notice F is F naught in both cases. G is just G in both cases.
Where you're writing the equation is out of the camera.
Oh, I'm sorry. I changed the camera setting to deal with the noise on the line. And I didn't notice you can't see that anymore. So the first one gave us F G naught. And now the second one is going to wrap around. You're able to see the whole K-map, right? Like, is this cut off?
A little, but you can still read it.
Better?
There you go.
All right. So here now we're going to deal with this like around the edge circling. And so since that around the edge circling, E changes within it, we can get rid of the E. But since F is 0 in both of those cases, and G is 1 in both of those cases, we'll keep the F is 0 and the G is 1. So we get F is equal to F G naught or F naught G. And that is the simplification of that circuit, which originally had 4 min terms and a lot of Boolean algebra, right? Like over here, we would have started with the original expression of E naught F naught G, or E naught F G naught. or E, F naught, G, or E, F, G naught. Sorry, my handwriting is really bad down there, but like we would have had this mess to use Boolean algebra on. I think based on what I was seeing, this would take you guys a little bit to do the Boolean algebra on. I mean, some of you might enjoy it. I kind of have grown to enjoy some of the Boolean algebra stuff over time, but I like the K-maps more because like we took that and turned it into that in a fraction of the time, especially once you get used to K-mapping. But K-maps were a technique invented at a later date than Boolean algebra originally was. All right. Oh, hey, look. All right, 4 variable K-maps are the largest K-maps we're going to deal with in class. Like I said, I've had students create them all the way out through an 8 variable K-map. That was like an option for an extension in person once, and they were like, I like K-maps, I'll do that for my assessment. I was like, all right, that's fine.
Hey, Mr. Schrago,
Yeah.
what are the numbers in the corner of all of the boxes?
Oh, it's basically what it's just showing you, okay, here's 0, this is min term 0. So like this line goes right here.
Oh, okay.
This
Cool.
line goes right here. I like to just think about it in terms of like, all right, well, here's W is 0, X is 0, Y is 0, Z is 0. Here's where that's true, that goes there.
All right.
Yeah, that's what they are. I just usually don't always mention them because they won't be on the assignments.
Hey, Mr. Schrago, how would we group it if there are 3 1s in a corner? So like the assignment that I'm looking at is it's a 2x4, and the bottom, and then there's 2 1s and then a 1 next to it. So do you split it?
Yeah, you can double circle a letter or a number, that is. And I think we'll see that in this one, is that you can
Fantastic.
you can reuse things. So yeah, if you're working on, all right, so it's going to show some groupings here. These are all your possible groupings in the one of size 4. Just notice that you can go around the edges on both sides. So keeping in mind these outer edges, these sides are connected and these sides are connected. There's just not a good 2-dimensional way to do it. The other one, this is the one most commonly missed, because these are all connected in the corners. Like when this thing would like fold so all the edges connected, the corners would all end up adjacent. And so you can do a circling around each of the corners, because you could like circle like that and like that. So this is a commonly missed one. So don't miss that.
Is that doable for everything, not just 16?
It's
square
doable for like
ones?
8 as well. Yeah. It's just only in a group of 8, it would just look like circling that and circling that.
Right.
And yeah, if you at any point doubt whether your circling is a legal move, this PowerPoint has literally every single option in it. So you can always come back and be like, all right, I have a 16 option K-map, 4x4. Let me go back and look and see if that's in the list of legal ways to circle numbers. All right, so for this one, they get really messy as they get big. That's why we're not going to have you go past 4 inputs. And I will mention to you, like the largest circuit you'll have that you might want to K-map is about 4 inputs. So as we go through this, the key is always going to be start with your zeros in the corner. Here's R is 0, S is 0, T is 0, U is 0. R is 0, S is 1, R is 1, S is 1, R is 1, S is 0. We're just going to follow the same procedure up top. Then just copy the ones over. Which again, that's how I like to do it, because if I remember, hey, here's my R is 0, S is 0, that takes me into this row. Now T is 0, U is 1. So here's T is 0, U is 1. I'll just go and keep looking through each of my ones. So if you're working on your own and you have this in your notebook, you might want to start just trying to make this, because this will take me a minute to copy in as well. You'll notice that if you follow this procedure, it helps because you can just move through your rows on the left here. So like I moved through all the ones in my first row by just looking through everywhere where R and S were 0. I knew that this section of the truth table right here covers this row. this section of the truth table right here is related to row 2, right? So that sometimes helps people when they're going through, is if they notice that they're like, hey, look, this stack of four rows on the truth table, that lines up with one of the rows on the K-map. So I did my first row, kind of took care of that. You can even put in your zeros right away if you're doing it in the row method like I'm doing. So here I'm going to see that there's, in this second row, I have 3 1s and I only have 1 0. And this allows me to shortcut a little bit because I can look here in this row. The only place I have a 0 is where T and U are also both 0. So right there, that's a 0. And I know I have 1s there because I can see that. And then 1, 2, 3. That's the end of that row. And look to my next row. And here I only have I have only 1 1 in this row. And that 1 1 in this row came from, oops, sorry, I jumped row. This is row 4. It's easy to make that mistake because you're used to it all going in order. And then when you hit this point, it turns around and flips because you need to have them both be 1s. That's the bottom. So I'll notice in row 3, I only have 1 0, which is again, when T is 0 and U is 1. T is 0, U is 1. There's the 1 0 in that row. The rest of that row was a 1. So you can see I have 4 1s in row 3, 1 0. Row 4, I've only got 1 1. And that 1 1 in row 4 is, let's see, 1 0. Oops, I put them in the wrong place. Sorry. Just got to double check yourself. I encourage you to double check anytime you're done with this. Just double check out of each row, one of them. And so right there, I was double checking. I was like, wait a minute. So double check and I'd be like, all right, when I need to make sure that when there's a spot where when R is 1 and S is 1 and T is 0 and U is 0, that's a 1. So here's R is 1, T is 1, or R and S are 1, T and U are 0. That's right here. That's a 1. And I can be sure. You do have to like double check this stuff when you build the bigger ones. It's right here. R is 1, S is 0, T is 0, U is 1. That's a 1. And all the other ones in that row are 0. It might take you a minute to build that K-map. Is anyone drawing that out on a note sheet or something, or trying to do it on like the little note section of the PowerPoint? I'll give you time if you are. All right. So the next thing we need to do with this is we need to figure out the circling. And you'll notice there's a ton of stuff on here that we could circle, right? Like I could just willy-nilly start circling groups however I feel, and I would get tons of little circlings in here and it would be a hassle. What I'll tell you to do is always start by looking for the largest possible grouping of numbers. And if I'm looking at this, I see that the biggest grouping I can see anywhere off the top of my head is a square of 4 numbers. So there's one circling. It's a square of 4 numbers. And now, kind of to hit upon what Mason was asking about earlier, is we can actually reuse some of these numbers. So right here, I saw a different group of 4 I could have circled. And just because a 1 was used in one of my circlings doesn't mean it can't be used in that other circling. So I'll include that 1 in both of those min terms, both of those circles. And I can use that trick with my wraparound procedure. Because I see that 1 there, there's nothing around it, but I could go around to the other side because they connect and circle like that. Same deal here, where I can reuse that 1 to loop around the top. If we're going through this, making our min terms.
Can you triple circle?
Yeah, you can circle a number as many times as you need to. Sometimes triple circling is going to be an indicator that you may have missed a larger circling somewhere, but you can certainly triple circle and it'll happen. Like there's no reason that this couldn't have been triple circled. If I had a 1 right here, I would have circled that whole section. Or I probably would have included it in that, but So yeah, triple circling is totally allowed. And I'm just going to start with my biggest min terms when I start writing my expressions. So I'll just start with the first one I made. And that's this box right here. I'm going to put a little number by each of my circlings to try to help you connect them with their min term. I just want a different color. So as I write the min terms for this, I'll just look at them and I'll notice in this circling here, R naught never changes. That first circling, R naught makes it through. S changes, so S goes away. T changes, so T goes away. Right, it goes from T naught to T. And so we're left with a U. Then I'll add a plus, that's an OR gate, to OR in my next expression. Down here, R changes, but S does not. So S is going to be in that last one. As a 1 because it's S standard the whole time. Then here I see T doesn't change, but U does. It goes from U to U naught. So U goes away and I'm left with T. Those two expressions. And you'll notice the larger your circlings, the fewer numbers you'll have. So now that was expression 1. Here's 2. And now let's get 3. I want you to notice that with 3, we're in a 4 input K-map, except now this one's only circling 2 total options. And what that means is we're not going to be able to cancel out as many parts of the terms. For instance, in this one, both times S naught was present. And now also T naught and U didn't change because we didn't go sideways at all. So that's S naught, T naught, U. Lastly, we got this one where it's RS on both sides because R and S didn't change as we went this way. We're all in one row. What did change though is that our T naught became T. So then we just have U naught for the last one. So that's 4. All right, this is K-mapping. Like this is the gist of what we're doing is you'll be having to make a K-map along these lines and translate truth table information into it, or you'll be given a pre-filled out K-map that you then have to do the circling on and write the logic expression from. Let's see if we've got anything more. I don't remember this presentation well. Oh, hey, look, they did my circlings. Oh, okay, the last thing we should mention are don't cares. There are don't cares present. And those are conditions that you don't actually care about. I know that sounds weird, but there are some situations that we've run into so far where there's something called a don't care. An example of that would be like in an alarm system, because that's one of our options that we're designing. Well, if the alarm is locked, right? Like the alarm, like let's say this alarm system has sensors on 2 different doors and an alarm enabled. Well, if that alarm is enabled and one of the doors gets opened, you don't care about the second sensor. That second sensor can be a 1 or a 0. Either way, you're setting off the alarm. And that's what a don't care condition is. It's when one of your inputs is irrelevant to what the output needs to be. And so that's represented with an X. Like right here, the condition where all the inputs are 0 is something we didn't care about. And what that means is we can either circle it to help us, because that would help reduce our logic expression, or we could ignore it because that wouldn't help us. Like it would be, we'd have to have extra terms to deal with circling something down here. And so we're not going to end up circling like this because it's a don't care. You don't need to circle it if it doesn't help you. Oh my. This is the same thing with don't care conditions. And you're just going to see like, look, you can use those don't care conditions to help you out by adding them into a circling, or you can ignore them because they don't help you at all.
So for don't care conditions, right?
Yeah.
Would you label, so like if you had your 2 inputs at the doors, yeah?
Yeah.
Would you label both of the inputs that say the door is closed as X?
No, so like can you see my little side? Oh no, you can't anymore because I changed the definition of my webcam to deal with some of the noise. Let me go back in my slideshow to find a kind of blank screen and give you an example. All right, I'm just gonna use the blank space here off to the side. So like in our theoretical like alarm system, right? We have our arms switch that arms the alarm. And then here's like door 1, and then like door 2 is a garage door. We're just gonna, for our lettering purposes. So we have our alarm, our door, our garage. We'll just build the truth table quick, and I'll show you where we would label the don't cares. So you see all the way at the bottom there still?
No.
It doesn't really matter. So like the place I would put a
Yeah.
don't care right here is, for instance, like, all right, our alarm is enabled and both of them are, our alarm is enabled and that's not on, right? We don't care about that. We don't care about a condition where just the alarms. We don't actually have a good example in
But
this
that would
one.
be a 0.
No, you're right. We don't have a good example in this one. I'm just trying to give you a condition where you like a situation where you don't care about. So like, here we go. Let's look at either way right here. Our alarm is on and that is. So like we could think of G as a don't care condition there, because right here in these, either way, that's a 1 and that's a 0. You won't really have to deal with it in your assignment. I'm just trying to give you an example of where you wouldn't care about. It's like when there's an input you don't need to deal with.
Okay.
So yeah, sorry, I don't have a better example off the top of my head. All right, that is it for this. Do you guys have any questions before we move into some work time? Although I realize that took us the whole block. Oh, and just as a note to people, on days where I whiteboard and I'm at the whiteboard, I literally cannot see whatever it is you wrote in the chat. My chat's just not visible when I'm presenting. So sorry. Anyway, so we got, since it's so late, you're welcome to stick around or leave a few minutes early if you want.
Then about the question asked in the chat, if you have just like 3 1s in a row, can you circle it? Because you said like it's not.
Oh, that's a really good question, Aaron. Yeah, it's a really good question. Let me quick draw up 3 1s in a row for you.
All right.
On one of these. So I'll go back to one of our 4 input K-maps because that's the most relevant place for that.
Your camera is off.
It's freaking, I'll fix it. That camera's dying. Why did that camera turn off? It's plugged in still. Yeah, it's so weird. All right, so Aaron, you're asking about like, what if you have 3 1s in a row? Like, let's say like that was a 1, that was a 1, and that was a 1.
Yeah, could you like circle all 3 of those or?
No, because it's illegal to circle odd numbered groupings. You can only do groups of 1, 2, 4. So what you can do though is you can do this, and you can do that.
Okay, cool.
So yeah, you reuse when you have an odd number, you just reuse some of the ones.
Cool. Thanks.
Yeah, no problem. All right, anyone have any other questions? All right.
Nothing. Have a good one, Trigger.
Yep, have a good one,
Thank you.
guys.
Bye-bye.
Later.
Thank
Also,
you.
Yeah.
thanks for the drop
Thank
off.
you.
Yeah, no problem. Bye, guys.